Let's share my screen. Everybody, can you see my screen?
Yes, Dr. Ali.
You see the slides about class projects. So again, this is the reminder for you that your project reports and PowerPoint files are due on November 17th. And today I have made a schedule for your presentation on the project. Like Manoj, Kamana, and Lakshmi, you will be presenting your project on November 12th. If you see that class schedule and syllabus, I have allotted 2 days for the presentation. One is November 12th, other is November 17th. So therefore, Manoj, Kaman and Lakshmi, you will be presenting November 12th, and then Sindhuja, Amani and Venkat, you will be presenting on November 17th, your presentation. Therefore, so each of your presentation can go about 25 to 30 minutes. So about 25 to 30 minutes, each of you can present, because 3 presentation. So then we will be done with the class time. And then simultaneously, you know that November 17 is the due date to submit that. Therefore, those who will be presenting on November 12, so after presentation, definitely you can submit the PowerPoint file. And those who will be presenting on 17, then you submit your PowerPoint file 17, or if you are done beforehand, you do that. But the report must be due by November 17th for everybody. I mean, that is the last step. That. So I will create Dropbox for both PPT file and then project report. So the reason to show this, that have you started looking these projects?
Yes, Dr. Ali.
Yes, Dr. Ali.
Okay. So Amani, so you said, so which software you are using? MATLAB?
Yeah, I think so. MATLAB would be easier for me.
Okay. So are you not learning those things?
I'm still learning, to be honest with you, Dr. Ali. It's not easy task for me.
Oh, okay. Okay. No, because it is just only about a month away. That's why I'm reminding you, each of you, from now on. And then Lakshmi, so you also responded. So which software are you looking? Is it MATLAB Simulink?
Yes, Dr. Ali, I'm using MATLAB Simulink.
Yes, so that will be appropriate for you.
Yes, Dr. Ali.
So you have to build both grid forming and grid feeding inverter.
Yes, Dr. Ali.
Yeah, together with the controller. Okay. And Venkat, what about
Yes, sir. Yeah, I'm also going through MATLAB.
MATLAB Simulink?
Yeah, working.
Oh, okay. Yeah. So in your case, you have to build the DC microgrid that will have the solar PV system and then battery energy storage.
Yes.
Yeah. So first you have to build the system. Yeah. So therefore, in this project, your task is just build a workable model of the DC microgrid. So you will not do any study like tangent stability or other. Just you build the DC microgrid and show that it is working, it is running.
Sure.
Yeah. So then Kamana.
Yes, Dr. Ali. I'm also reviewing paper,
Okay.
and I have already downloaded Simulink, MATLAB Simulink, and I'm learning that now.
Okay, yeah. So you just need a solar source and then that AED device. Yeah. So that will be fine.
Yeah, sure, Dr.
And then Manoj.
Yes, Dr. Ali. I'm thinking about building the 5G enabled at least network in the NetSim.
Right. So
And
is that NetSim working properly?
yes, Dr. Ali, I tried after you sent it, so it was working well.
Okay. So you fully followed their process that is mentioned there.
Sure, Dr. Ali. I'll just go through all the tutorials and try to build a
No,
network.
I mean just for downloading purpose and running, you just followed their step.
Yes, yes. I just followed what is written in the
Yeah.
email.
I mean, at this point, I am just verifying that it is working or not.
Yes, Dr. Ali, it was working.
Oh, okay. Then next is implementation for your research. That is the different thing.
Yes, Dr. Ali, sure.
Okay. So therefore, everybody, please, you now I mean, seriously, you all start, and then like every day I will be asking you about the progress until the end of the project, until November 17th. Okay, so with that, let's stop this one. Okay, now can you see today's topic, effect of optimal reclosing technique of circuit breakers on transient stability control in power network. So because we are looking the stability, there is another topic, very important thing, effect of optimal reclosing technique of circuit breakers. So you all know that about circuit breakers, when there is a fault in the system and that fault causes the transient stability issue, then the very first reaction comes from the circuit breaker. Circuit breaker opens after a certain time. There are some prescribed time depending on the system, depending on the country. And then there is prescribed time, the circuit breakers reclose. And then depending on the permanent fault or temporary fault, they might reopen again. We discuss those things. But today, the topic is effect of optimal reclosing technique. So as I said that circuit breakers once open, then again it will be reclosed, but that is prescribed time, like fixed time. Okay, let get reclose again after 1 second or after 1.2 seconds. So therefore there are varieties of network, power network, and there are varieties of rules and regulation. So, but that time is fixed. But optimal reclosing technique, this is not fixed. Therefore, we will be looking at what is that optimal reclosing technique, and it has some benefits over the conventional technique. So therefore, now everybody see, this is that conventional reclosing method. I mean, the thing that I said, that conventional auto reclosing techniques, I mean, the reclosing system is automatic. It is automated. Both circuit breaker opening and reclosing, those are automated. But those techniques adopt fixed time interval reclosing. That is the circuit breakers reclose after a prescribed dead time, which is set to a constant value. So now, what is the issue with that? I mean, my topic is optimal reclosing, and now I am contrasting with conventional reclosing. So what is the issue with the conventional reclosing? Of course, conventional system is working, you know, that over the years, over the decades and decades, and system is running well. But if you apply the optimal reclosing technique, then your transient stability performance will be much better. That is the thing today we will be looking. So we will be looking what is the optimal reclosing technique, how is it working, and how it is improving the transient stability. So now what is the issue with that conventional reclosing technique? So I have written something for you, that since the transient stability is dependent on the generator state of reclosing instant. So in some cases, it might happen, conventional method may cause unstable state, especially in case of unsuccessful reclosing. So, you know, unsuccessful reclosing means braking resistors attempted to get reclosed, but it was observed that there was permanent fault. So before several class backs I was discussing the impact of permanent fault, because the fault is still going on, even though that automated circuit breaker attempts to get reclosed, but again it will be reopened. Again it will be reopened. So especially in those cases, that conventional method does not perform well. So even the system might be unstable. So that's why to maintain the system synchronism, I mean power quality, transient stability, the circuit breaker should be reclosed at optimal reclosing time. So therefore that ORCT, that is the abbreviated form of optimal reclosing technique, where the system disturbances after reclosing operation are restrained effectively. So it has been shown in some experiment that depending on the fault type, especially in case of unsuccessful reclosing, so even though circuit breakers get reclosed by following the conventional technique, but after that, after reclosing, still there is stability issue, like system was oscillating or still there was disturbance going on. That's why we need the optimal reclosing technique. So now that is the question, that what is that optimal reclosing technique? How we will reclose the circuit breakers, that thing we'll be looking. Now, if you see the literature, there are various types of techniques. You see, I have written that various optimal reclosing technique. Sometimes you will see total load angle, it is called TLA method, total kinetic energy method, variable dead time control method, then variable dead time auto reclosing using artificial neural network, adaptive reclosing algorithm considering distributed generation. Like if you have the distributed generation, means like solar energy, wind energy, then you need different technique. Transient energy function method. And then again, there is neural network based adaptive single pole auto reclosure method. So these are the optimal reclosing method. But among all these methods, that number 2, total kinetic energy based method, that has been shown to perform the best for any power network. Therefore, all methods work. I mean, here is the thing. Each of these methods are better than that conventional technique. But then among all these methods, the total kinetic energy method performs the best. That's why in today's class, I will be showing you, I'll be discussing this one, total kinetic energy based method. Based on that method, how we can reclose the circuit breakers. That is our proposition today. Now, this one, what is that total kinetic energy based optimal reclosing method? So meaning that by the name, as you can guess, that first we have to calculate the total kinetic energy of the system. What is the total kinetic energy? So in a system, in an interconnected power network, there can be many generators, 100 generators. Now you have to collect that kinetic energy from all the generators. And once you get that total kinetic energy information, and then you have to apply some technique, that technique will tell you whether this is the optimal reclosing instance or not during fault. So therefore, what is that method? This is the method. Everybody see that second line. According to this method means total kinetic energy based method, the optimal reclosing time is considered as the points which meets the following two conditions. Now there are two conditions, number 1, number 2. So therefore you have to look the total kinetic energy response that you will be calculating by getting signal, speed signal from all the generators connected to a network. And then you will be noticing whether that kinetic energy signal, total kinetic energy signal, is meeting these 2 points. What is the first point? The point when the total kinetic energy oscillations of the generator without reclosing operation becomes the minimum. So I am coming that point, and then it says the value obtained from condition 1 must be greater than TCB, reclosing time, as shown below. Now, this is therefore the first of all, before going 1 and 2, it is talking about the total kinetic energy. Therefore, so before we discussed like how to calculate total kinetic energy, therefore everybody, you know that this is the total kinetic energy equation, and that kinetic energy is half Ji omega m square. Ji is the moment of inertia. We solve the problem. So you know this thing well. That is the method. But once we get the total kinetic energy of a system, of a power network, what you will be looking? You will be looking this profile. That is the method. So the method is that you see this axis time, and then in this axis total kinetic energy. Therefore, the fault happened. So initially, you see, there is some constant value, 2.58. If there would not be any fault in a system, then for example, that 2.5 joule, I think it will be much more, not just the joule. Oh, there is 10 to the power 9. Yeah. So 2.58 multiplied by 10 to the power 9 joule. That's why it is written joule, several hundred megajoule. And then that value will be constant. Once there is any fault, so we are assuming there is fault here 0.1 second, and you see total kinetic energy went up. So this is, total kinetic energy very similar to speed change. You have noticed that in case of synchronous generator or even induction generator, following a fault, speed goes high. Now total kinetic energy is build up is calculated with the help of speed, like half mv square, half gi omega square. That's why total kinetic energy response also very similar to speed. You see, fault happen and then it is going up and then coming down. And after some oscillation, like around after 15 seconds, it looks like it settled down. It became original value, 2.58, the 10 to the power 9 joule at this level. Now, what is that optimal reclosing technique? Now come back here. It says, now read everybody point on. The point when the total kinetic energy oscillation of the generators without reclosing operation becomes the minimum. So therefore, you have to look that curve, total kinetic energy curve, and then you have to see which one is the minimum point. Now, fault happened, circuit breaker opened, you did not reclose the circuit breaker. The condition is without reclosing operation, because you want to calculate the optimal reclosing instance. Still, you did not reclose the breaker. Fault happened. You captured all the information. You calculated total kinetic energy. I mean, everything is happening because this is digital. It's everything will be happening within millisecond range. You got this response. Your controller, your system has this system. It is calculating, your master controller. You are looking this one. You are looking means automatically it will be look which one is the minimum point. Now everybody say this is our minimum point. Then again there is minimum point. There is minimum point. So there are many minimum point. So what is the rule is telling? The point when the total kinetic oscillation of the generators without reclosing become the minimum. So therefore, the algorithm will be first you will be looking this minimum point, and at this minimum point, what is this value, corresponding value here? Like here, although it is shown in big scale, like 0 to 5, 5 to 10, but definitely it is some value. I think actually I have written that point is 0.889 second. The optimal reclosing time, the point at which total kinetic has the first minimum. This is the first minimum point. Now the question is, this statement does not say it is the first minimum point or second or the third one. It just says that becomes the minimum when. So therefore, the algorithm will look first minimum point. And for example, this point on this axis is that 0.889. And then once you get this value, that this is 0.889 second, then you compare that value 0.889 with this equation. What it says, the value obtained from condition 1 must be greater than TCB. So this means that this TCB will give you a value. I am coming that what is that? This TCB value will give you a number. Therefore, for example, you got TCB value 0.6, just an example. But then 0.6 is smaller than that value. So therefore, you cannot choose this one. Therefore, you must be looking this one. So because it says, oh, sorry. So if this is 0.6, already this is smaller, so then that is fine. So I told the opposite thing. It's saying the value obtained from condition on must be greater than TCB. So therefore, I was giving the example. If you notice this is 0.6, 0.7, that of course that is smaller than 0.889, then that is the minimum point. On the other hand, first point was 0.889, but after calculating here, you got like 1 second or 1.2 second. or you get much more smaller value. So you don't know what will happen. Then accordingly, you may need to go to the second point or third point. So you just need to meet this condition. Now the thing is that what is that? It is TCB, reclosing time. Now this is called on empirical equation. This is power engineers, especially those who are the experts of circuit breakers. After a lot of trial and error, they have explored this equation, this definition. That okay, that at least TCB should be this value. Therefore, if the value obtained that is greater than TCB, only then it is safe to reclose the breaker. If not, then don't reclose. So now in this, again I am coming this one. In this equation, as you can see, this is just a number, 10.5. This is kV over 34.5. That is also numbered. kV is that kilovolt. What is the system kilovolt? I mean, the system for which you are dealing with this total kinetic energy, what is the available kV for the system? Is it 500 kV? Is it 20 kV? Is it 50 kV, 100 kV? What is this number? Or 1000 kV? It depends on that. Therefore, depending on that number, this value will be changed. Therefore, for example, I am telling exactly what is the TCB. So according to this one, you see this plus this, then in parenthesis, after parenthesis, I have written cycles. This means this is not expressed in time of second or millisecond. This is expressed in terms of cycle. Now, for example, I showed this picture based on this diagram. So everybody see, before we discuss this one, IEEE 9 bus system, we discussed some questions also. So as you can see, what is the base for this system? It is written 50 Hertz, 20 kV, 100. Therefore, 20 kV is the voltage here at the generator terminal, here or here. This means for this system, that voltage in that equation will be 20 kV. I mean, the system for which you are calculating this one, of course, that information will be given to you. So therefore, for example, it is 20 kV. Therefore, that number is directly expressed in kV. You see kV. Therefore, here you have to put 20. Therefore, everybody calculate in your calculator. If you put 20 there, then what will happen? So therefore, you see, so I'm doing like 20 over 34.5 and then plus 10.5. So you got 11.079, and then it says this is cycles. This means that the value obtained from condition 1 must be greater than this dB. This means that the circuit breaker closing time must be greater than this value, which is 11.07 cycles. Now, because this is the 50 Hertz based system, everybody say, it says 50 Hertz. The system can be 60 Hertz, no problem. So based on the 50 Hertz system, the value of one cycle, where is that? So the value of one cycle is 20 millisecond. One cycle value is 20 millisecond. It is coming time equal to 1 over f. If you do like 1 over 50, you will get 20 millisecond. Therefore, 20 millisecond multiplied by that cycle that you got. So we got 11.07 cycle, then multiplied by that 20 millisecond. So I am getting 221 millisecond. So this means then if you divide by 1000, so 0.22 second. So therefore, this means that this timing, TCB timing, by calculating this one, I got that 0.22 second. Now it says the value obtained from condition 1 must be greater than TCB. This means you must wait until that time, until 0.22 second to reclose the breaker. You are not allowed to reclose the breaker before that time. That is the meaning of this. So now that condition is meeting properly, as I said, the first minimum point, this one, 0.889 second. So this time is bigger than what we are getting here. It is 0.221 second. Now you can reclose the breaker at this point. Now, if you notice that no, that time that you got much larger than this one, this number, then you have to see this one. So therefore, this is the minimum time that you must wait to reclose the breaker. Now, that is the thing that why I have to wait until that time. Why? What is the basis for that? So that thing I will explain you now. Everybody, do you understand so far?
Yes, Dr. Ali.
Yes, yeah. So just listen carefully, then you will get, and this is pretty interesting and the new technique. So the thing is that why we need to wait and what is the actual significance of this one? It says the TCB reclosing time. So therefore, let me take you to the board for a minute. So for example, the line is going on and then this is the circuit breaker. Just I am giving simple example. And then circuit breaker, you all know it's like a switch. This is circuit breaker. And the normal condition when current is flowing properly, everything is fine. And then circuit breaker is closed condition. And once fault will happen, for example, somewhere there is fault here. There is some fault here. And then circuit breaker will open. So therefore, this got open. Now, and then we are talking about the reclosing. When to reclose? I mean, we are discussing about this reclosing. Now, the thing is that, I am not sure that I have told it before. The thing is that once circuit breaker gate opens, actually a low impedance path is created. It is not really like open circuit. It opened, I mean, it disconnected the fault, but still it is called the arc, ARC. Arc is formed. So arc means this is called the low impedance path. Low impedance path. That is called the arc. This means that if you put your finger here, like you will feel, you might get shock because it looks like there is with little impedance and something is flowing. I mean, majority of the current got disconnected, but still something is there. And that is harmful, that is dangerous. Now the thing is that arc is going on. Arc means like this type of connection. It is present, it is going on. And then prescribed time is, okay, you open the breaker and let's say the prescribed time is after opening the breaker, within 1 second, you have to close the breaker. And then the circuit breaker got closed. It is automated. But you reclosed it, but still the arc is there. Then that is the dangerous situation. Therefore, in real practice, what is done, before reclosing the breaker, it is checked whether this arc is still present or arc has been extinguished. That's why typically there is what is called sulfur hexafluoride. Probably you know from this one, SF6, sulfur hexafluoride. From the chemistry, you know, it is called the SF6, sulfur hexafluoride. There is on sulfur hexafluoride gas that is given here. That extinguishes the arc. But that sulfur hexafluoride takes some time to extinguish this arc, to end that arc, to deplete that arc. That is that waiting time that was given by that equation, that TCB, that circuit breaker reclosing time was that one, that 10.5, that plus and that kV over that 34.5, and then that is in terms of the cycle. And as I said, for 50 Hertz on cycle means 20 milliseconds. Therefore, power engineers have confirmed that this is the time, at least this is the minimum time that you must wait before reclosing the breaker. That is the arc extinction allowing time. Therefore, I think probably you have heard that there are different types of circuit breaker. sulfur hexafluoride. This is pretty common. Air blast circuit breaker. That there is only media air. There is no sulfur hexafluoride. Therefore, because arc is formed, it is natural. You have to extinguish that arc, and then there are different media. Sulfur hexafluoride, air, or other type of gas, neon circuit breaker. Accordingly, there are varieties of circuit breaker. I mean, that circuit breaker itself and protective relay, it's a completely like different subject, different topics. Switch gear and protection under that subject. So everybody, could you follow me what I'm saying?
Yes, sir.
Yes. So the one circuit breaker open, for disconnected, but still there is low impedance path going on. You have to allow that time, let it get extinguished. That is that waiting time. So okay, then I am taking you that. Yes. So that's why the value, that minimum value that you got. Now you will be comparing. First fault happened. You constructed this waveform, total kinetic energy. You will be looking the where is the minimum point, like one minimum, two. There are many. You first look the first minimum and make sure that this time is greater than this time or not. So if that time is greater than this time, meaning that by then that arc has been extinguished. Now it is safe to reclose the breaker. That is the meaning. If not, then you will be going the second point. That is the rule. Therefore, typically, like I have seen, I myself have done some simulation for various systems, and not just this system. Like you may need to go up to third point for comparison. It depends on the system. So as you can easily guess, like here I calculated that one based on this system, 20 kV. So easily you can guess if this number is higher, 500 kV, definitely this result will be larger. Then at that time, that first point is not enough. You have to go second point. If second point is not enough, go the third point. So I have not seen to go beyond third point. Typically, like first point or second point, it works. So this technique is called that optimal reclosing technique. So it is not any fixed thing. It is based on the waveform based technique. And it works very nice. Yeah, like I myself have done some work. I have some publication and I have seen some other researcher. It works very nice. Therefore, you all will be remembering this one. If you just Google optimal reclosing technique, then many articles will pop up about this method, kinetic energy, including some of my papers. So I think everybody understood. And then now based on that, I think at the beginning, I have a few questions. How would you answer this one? That why is optimal reclosing of circuit breakers preferred? So how would you answer this one? Who likes to answer? Amani?
Yes, Dr. Ali.
So what would be your answer, that why is preferred over the conventional reclosing method?
I think that's to make sure it's safe to reclose the circuit before, I mean, to make sure it will not make any damage for the
Yes.
net connection.
Yeah, of course, that is. And then what is the ultimate goal? What we are looking to improve the transient stability.
Yes, sir.
Therefore, that method is preferred because it has been noticed that by applying this technique, reclosing technique, transient stability performance is enhanced as compared to the conventional method. So therefore, everybody see the answer is optimal reclosing of circuit breakers is preferred because it improves the transient stability, or its performance of improving transient stability much better than the conventional system, conventional method. So then what is the conventional method? Conventional method is based on fixed timing. Now, I was telling you that circuit breaker reclosing, conventional method also looks that arc extinguish time, but conventional method is fixed. It says, okay, let's reclose it after 50 cycle, or let's reclose it after 30 cycle. Therefore, depending on network, depending on country, there are various rules. I mean, of course, every country allows that time. I mean, wait until that time, arc extinguishing time. But after that, it is kind of fixed. It is conservative. This means that if it would be reclosed much early, the thing I have noticed through simulation, If you just wait until that arc extinguish time, and if you immediately reclose, then the performance is much better. But the conventional system, because it is predetermined, it is fixed, it likes wait 1 second. I have seen 1.4 second, longer waiting time. Because as early as you can reclose the breaker, that is better for the system, for the connected people. If it is temporary fault and then arc has been extinguished, your fault has been cleared, then why not reclosing it early? Why we have to wait? That is the limitation or drawback of the conventional system. And that's why I have noticed like last 20 years, there are lots of research has been done on that optimal reclosing technique. So therefore, some countries have adopted this still optimal reclosing, but most of the countries still goes with that conventional method. Because you have to put these new methods, there is some replacement costs of that breaker and this type of algorithm. So therefore, still some countries follows that fixed reclosing method.
Sir, conventional means manual reclosing. That is what you mean.
No. That is also auto reclosing, but fixed time. See, conventional auto reclosing techniques. That is auto, not manual, but adopt fixed time interval reclosing. Meaning that I was showing you that on the whiteboard, circuit breaker open, and then exactly it will wait until that fixed time. Now that fixed time, now circuit breaker reclosing time can vary from 30 cycle to maximum 60 cycle based on the system. Like here MLGW, I have asked MLGW, they wait 45 cycles. 45 cycles.
Yeah, yes, yes.
That is the wait time after opening the breaker. Like everybody say, first fault happen, circuit breaker open. This thing reclosing after opening the breaker, how much? That thing we are discussing after opening. And then first circuit breaker opens within 5 cycles. So 5 cycle is the maximum opening time. Fault happen, circuit breaker should open, that maximum time is 5 cycle. Therefore think, if it is 50 heartbeat system, then one cycle is 20 millisecond. So therefore 5 cycle is 0.1 second, 100 millisecond. So that is the maximum time. And that is the critical time, critical clearing time. You remember at the beginning of the semester we talked critical clearing time, CCT. That is that point on time. Then the system will still maintain synchronism. If you delay much more longer, then by then connected device will be burnt out. There will be many damage, stability issue. And once you open the breaker, because there will be arc formed, you have to wait some time, arc extinguishing. That's why early days, like 50 years, 100 years, more than 100 years ago, power engineer thought because we have to allow the arc extinguishing, let wait long time and make a fixed time, let's say 1.2 second. That thing I am talking that is like too long. Yeah. You may not need to wait until that time because arc might be extinguished much early, but because you are using, technique is automatic reclose, but automatic reclosing will happen after a prescribed time. That is the issue or the limitation of this technique.
Sir, these auto reclosing breakers are mostly used in the distribution systems, right?
Yes. So therefore now the thing is that, for example, because it depends on country to country, these techniques vary. Now some countries they are using the conventional reclosing, but they have used such a method that their waiting time is less. For example, reclose after 30 cycle. They have thought that okay, no, if they wait just 30 seconds, that is fine. So therefore they have fixed their time 30 cycle, that is enough. But I have seen that up to 1.6, up to 1.8 second waiting time in some power network, that is too long. So that's why that optimal reclosing method is coming. That, for example, that kinetic energy based method, you just need to calculate total kinetic energy by using this technique that you all know. And then if you can produce this response, and then you see the minimum point, and then compare with that equation, arc extinguishing time, and then either this point or this point. If you reclose, then always it works better. Okay. Oh, sorry. Then I was here. Yeah. So everybody, could you follow me so far?
Yes.
Yes, Dr. Ali.
Yes,
Yes.
Dr. Ali.
Okay, great.
Sir, nowadays the breakers are mostly programmed, right? The
Yeah,
substations.
program, mostly program, but mostly program, I mean digital breaker, but still this optimal reclosing technique has not been adopted in many breakers. That can
Yeah.
explain. The breaker are automated, and those are automated, but still this technique has not been adopted.
Yes,
Okay,
sir.
sorry.
Yes, sir. Thank you.
Oh, sorry. Okay. Everybody read this on middle, and there is on a numerical problem. Assume that on a 500 kV three-phase transmission line of a 60 Hz power network, a three-phase to ground fault has occurred. The circuit breakers on the line operate properly under fault condition. So pretty good. What should be the required reclosing time of the circuit breakers, allowing the deionization of the fault arc? Like I was telling you, the arc extinguishing, that is basically deionized. As long as there is arc, it is called ionization form. Then you have to deionize, allowing the deionization of the fault arc. So where kV indicates the line-to-line RMS voltage of the system. So can you tell me that what should be the required reclosing time? So from this equation, therefore everybody put this number 500, just 500. Keep in mind, you don't need to change into volt. This number is directly kV. Don't make that mistake. So just that 500. When it is 20 kV system,
About,
then put, sorry,
25 cycles.
yes, about 25
and
seconds.
then tell me in second, how much in second? That is the thing. Please tell me in second.
So can you please remind me how many seconds each cycle?
So this is for 60 Hertz system. You see the very first line, you are doing for 60 Hertz.
Okay.
So 60 Hertz means that 60 cycles per second, right? That is the meaning of Hertz here. So in 50 Hertz, 50 cycles per second. So therefore you can, for the everybody, for 60 Hertz system, calculate what is the on time period time. What is the capital T time period of the waveform? For example, we have sinusoidal waveform. For 60 Hertz system, calculate what is the value of one cycle. What is the value of T?
0.01 here.
Yeah, 0167, right?
Yeah, 0.161. Yes.
Therefore, 1 over, everybody see 1 over 60. 1 over 60 is 0.0166. That is the second.
Yeah.
Now, how much cycle you got, you say? How many cycle you got?
25.
25 cycles.
Okay, so
So,
therefore you multiply that time 0.0166 multiplied by 25.
I got 0.417.
0.17?
0.417.
Yes, I got that. I got same.
You are right. Yeah. So therefore, that is the question. That is the answer. So therefore, everybody see what should be the required reclosing time. So what you do answer based on the result that you got 0.417. So what you do tell? Question is that what should be the required reclosing time? So therefore, what we learned, I mean, again, go back. What is the point number 2? The value obtained from condition on must be greater than TCV. This means the reclosing time must be greater than this time. For example, if you get this is 0.1 second, then circuit breaker reclosing time must be greater than. You must wait until that. So therefore, in this problem that you are doing, you all got 0.417. So when I am asking what should be the required reclosing time, you have to answer that it must be, the reclosing required time must be greater than 0.417 second. Do you understand?
Yeah.
Can you repeat, please?
Everybody, could you follow me?
No, Dr. Ali, can you repeat the last?
Okay, so therefore we all calculated that TCV
Yes, sir.
value at that 0.417, right? Second. So meaning
Yes.
that time is to deionize the fault arc. That time is to extinguish, to finish that arc, fault arc. So circuit breaker should be closed after that time. At least you have to wait that time. This is the critical time. So that is the meaning that what should be the required reclosing time. So you have to just tell that circuit breaker reclosing time should be greater than 0.417. I mean the result that you got. Meaning that, so this equation is calculating what is that time, deionization time. That is the calculation that we got from the TCB. Now do you understand?
Yes, Dr. Ali, I got it. Thank you.
This means that we have to wait at least that time. That is the question. What should be the required reclosing time? We'll be telling that required reclosing time should be greater than that TCB value, which is 0.417 second. You must wait, even the little bit, like one more cycle. You have to wait one more cycle. Like you all got 25 cycle, you can reclose at 26 cycle. That is the meaning of this.
So this value changes based on the type of circuit breaker.
And no, just look the equation only based on the kV.
Yeah, yes.
Based on the kV, and then what is the frequency of the system. Two factors, because it is like cycles, this number. But then if it is 50 hertz, you will get some number. If it is 60 hertz, it will be different number. That's why accordingly, every country has some design, their system, and accordingly, a circuit breaker is placed. So therefore, this conclusion, as I said, this is empirical equation for engineers. I think at first this equation was developed somewhere in Europe. They first explored, and then they said, no, this can be applicable to any system. It just depends on the system kV and the number of the cycles and what is the frequency of that country. That's why you see these magic numbers, 10.5, 34.5, because after a lot of trial and error, after several years before they convert this equation. This is the time. Because you want to make auto reclosing, that thing you are telling. Therefore you need a proper calculation. How long should we wait? This is the like, you must wait that time. Okay, then moving forward, you see, then now I'm taking that point that in the literature it is shown that optimal reclosing of circuit breakers provide better transient stability control over the conventional reclosing. But is there any foreseeable obstacle to implement this technology? Explain your answer. Therefore, as you can easily guess, that this system, optimal reclosing of circuit breakers, we looked at total kinetic energy. So what can be the foreseeable obstacle? What you can forecast to implement this technology? So the first thing is that you have to get the total kinetic energy, right? So this is the method. So therefore you can argue, no, this is like simple, this is just the math, that is fine. But then how you will implement in the system? That time, you remember once I was showing you this diagram, that closed loop control system, total kinetic energy from all the generators are dispersed at various places. I mean, it is not like always unilinear or on the same line, they are scattered and there are 100 generators. So here that technique, control technique, this is central control office where you will be calculating the total kinetic energy. And you remember before I discussed this method, that because kinetic energy half Ji omega square, you need the speed information. And you are collecting that speed information from all the generators and you are passing through filter, because those are the analog signals, and then you are converting into digital with the help of analog and digital light signal. But this is one place and all generators are placed at different places. From here, the distance, they are not equidistant. So you have to make them. And because they are not equidistant, so therefore you might not get all the signals together. That's why you need the help of the GPS. And that GPS receiver will make the time and phase synchronized of all those signals, so that there is very little delay, like 1 microsecond, 2 microsecond. In United States, that GPS has the accuracy of about 1 microsecond or 2 microsecond, like that. So therefore, you collected those signals. They probably have 5G will work much better. So Manoj?
Yes, Dr. Ali.
Yeah,
Yes.
I think the 5G will be much better than even the GPS. I don't know well, but I think so. we can
Yes,
put
yes,
that
that's
we
true.
can put have 5G for
The
this.
same system we saw in the like cyber security model, right, sir?
Yeah. Yes.
Yeah,
Okay.
I
And then,
remember.
yes. Right. So therefore, then everybody see, then you calculated the TK here, and then you will be, then you see, I am taking on, I am going to the circuit breaker, ORCT technique. Then there will be ORCT technique. Technique means once you calculated this one, then produce this curve. That you can do easily through coding. You will be getting this one, and the real algorithm will be checking this one and comparison with this one, what you are getting. So this is just you see calculation, and then this thing you can see. The main goal is to produce this one and compare these minimum points, whether those minimum points are greater than this one or not, whether it is meeting those two conditions or not. Now the thing is that once you do that, and then you got the technique, and then that effect is going in the circuit, I mean through the circuit breaker, and system transient stability is maintained or enhanced. But that was the question there. What was the question here? But is there any foreseeable obstacle or drawbacks to implement this technology? So therefore the answer could be yes, because you see, it is dependent of several components. What if you don't get the signal properly? Or what if you did not get the signal from 1 or 2 generator? So that is not giving you the proper TKA. So if you don't get all the signal properly, or all the signal is not time and phase synchronized, then you might not see this type of curve, or you might get the wrong curve. For example, it did not come downside, it only went upward. Then you cannot implement this technique. So this means that is the question, that according to that technique, you have to fully collect all signal. Your system should be very robust, so that you get, and then it properly calculates, and you don't make any mistake in the calculation. So you fully follow these steps, using what is the MV rating, what is the H value of each generator, because the equation is half Gi omega m square, and Gi is this one. So if you don't make any mistakes, then you will be getting the correct response, and then that will give you the correct number, and then that is set. So everybody, could you follow this question, answer to this one?
Yes, sir.
So therefore, I mean, if you are asked this question in the midterm exam or any exam, final exam, then with the help of this diagram, you can explain. So therefore, as I said, that if you Google that optimal reclosing, you will be getting many articles, and so you will get my few articles. So I would recommend you all to download this paper. This is like I was the first author, and I published on in IEEE transaction power system in May 2008. And that time I was in Canada. I completed this work while I was in Japan. So that's why you see that last person, Junji Tamura, he was my advisor. And that Toshiaki Murata, he was my second advisor, co-advisor. And I'm the first author. I completed when I was a postdoc fellow. I completed this work in 2006. And I submitted the paper in 2007, sometime, probably September, October. But then going to Canada, it got finally published. So therefore, I would recommend you to Google this one, and you download this one and read this one. This is about that optimal reclosing technique. So in that paper, what I did, I improved the transient stability by combined effect of fuzzy logic control, superconducting magnetic energy storage, considering coordination with optimal reclosing technique. Now, in many cases, you will notice that you don't need anything, any energy storage or any braking resistor or any SBC, any other device, fault current limiter. Depending on system, sometimes just this method, or depending on network, sometimes you need the coordination or combination of this technique plus, for example, braking resistor, this technique plus an energy storage device. That's why that is my motivation when I use the coordination, I mean optimal reclosing technique plus that fuzzy control SMS, and then I got much improved result. And then at that time it was very good and very hot report, and that's why it got published in IEEE transaction power system. I mean now it has been about 12 years, so some other improved technique might have been developed as well, or some researchers are looking what if what can be the other parameters in addition or except the total kinetic energy. Now the thing is that as you can easily guess, because I am taking the total kinetic energy and then I showed you this picture, all are the synchronous machine because I am taking speed signal. Now what if the system to have both synchronous machine, induction machine, and then solar system? Then what? If you have the solar system, then you cannot apply this technique. You understand? Because you need to collect the speed. If you have the solar, then how you would get the speed? Solar is a static device, you know. So that time you cannot apply. Then you can argue, no, I will apply partially. I will only collecting signal from the synchronous machine. I will not take any signal from the solar or the wind or the other form or the fuel cell. I will not take any information from energy storage. Then you might not get the correct reclosing time. That might affect your result. So that time, the best thing is that to consider the voltage signal. Because for example, if you just see this diagram, this is synchronous machine, this is synchronous machine. They all are providing power at these buses. So at these buses, speed is not available, but voltage information is available at each and every point. Speed is only available here. Now, if you have a, for example, solar system or fuel cell system, which are static power sources, they generate power voltage, and then once you connect it here by properly maintaining all those parallel connection method, then definitely you can see the voltage here. So then you can say, instead of the total kinetic energy, you can use the total voltage at a particular bus. For example, I will be collecting all voltage information here. I will be looking the voltage, or you can say I will be looking only the terminal voltage of all the sources. These three plus any PV sources, terminal voltage. And that you will collect at a certain point. For example, the similar method, you can collect all the voltage signal, terminal voltage from all the sources, not just synchronous. And then again the same method, you look the total voltage, and then you can find out some technique, and then that you can apply for reclosing of the breaker. So therefore, keep in mind that when it is total kinetic energy, because kinetic energy depends on half Ji omega squared, because this equation, then definitely this is applicable to rotating sources only. So it is not applicable to static power source like solar or energy storage or the fuel cell system. So therefore, everybody, I must recommend you as long as you are using university credential, then you can download this one. Yeah, if you try from home using your own computer, then it will not allow you. It will ask you money to pay. So that's why you use university credential and you download and then read this paper. So is everybody fine so far?
Yes, Dr. Ali.
Yes, Dr. Ali.
Okay.
Yes,
And
sir.
then, yeah, okay. And then again, going back. So when the question is, what are the foreseeable obstacles or drawbacks to implement this technology? So you understand the challenge of collecting those signals. Whatever the voltage or speed signal, of course it is challenging. because you need lots of the components. So and then the other thing is that there will be some time delay. So you remember last class you are presenting your paper and you showed the impact of the time delay, right?
Yes, Dr. Ali.
The same thing. So here there can be time delay because you are collecting signal and these are the analog signals and it is going through the digital reset filter. So those filters some sort of, you know, 1 over 1 plus st, there is some time constant. And then again, these are the converters. So there is some delay here. GPS receiver, as I said, 1 to 2 microsecond, but still that is delay. And then this is a computer, big computer, central control office. There can be some delay here. And then again, when it will be circuit breaker, that has some delay. So therefore, there can be several hundred millisecond delay. Therefore, that may have the impact. So therefore, the other answer to this question, when I'm asking that, what is the foreseeable obstacle? Of course, it is challenging, difficult system to get that kinetic energy. Also, there can be some sort of delay. And if it is too much, then there is impact on the system. So therefore, another thing, another topic, like you were presenting that paper last class, and if you Google the impact of time delay on the transient stability of power network, you will get a lot of articles. So everybody, if you can Google, like for example, this title, effect or influence of time delay on the performance of transient stability control in power network, you will get a lot of article. So therefore, there's some discussion about that one in continuation to this one. Sometimes you might get the word communication delay instead of the time delay. It is the same. And that time delay, therefore here you see, like this is a control technique, optimal reclosing technique that involves several components. Similarly, in power network, in integrated power network, there are varieties of controllers. And those are communicating. You have seen like phasor measurement unit. Those are like communicate with the SCADA system. So similarly, in the power grid, there are varieties of signal which are being communicated, sending data or information to and from the controllers. And then there can be some delay. And those delays have some adverse impact. So I will show you in terms of transient stability of a power network that the delay has also some sort of impact. And it depends on what is the system, what is your controller input and output. Depending on that, the delay value increases and that may have impact. And even there are examples that the system might be unstable. And then this is additional thing. If you remember those who attended in modern grid class in last semester, we discussed this thing also, that if now system is being controlled through internet, then there can be issue of cyber attack and cyber hacking, cyber threat, and that might cause further delay. Like DDoS attack, distributed denial of service attack. So can you remember like Manoj, Amani, Venkat?
Yes, Dr. Ali.
Yes, Dr. Ali.
Yeah. So therefore, if there is, so therefore in this class we are not talking about cyber attack. Like we are talking that in power grid, even though you don't think about the cyber attack, modern power grid, conventional power grid, still that is too complicated. And there are varieties of controllers like that. And then that think about that fuzzy logic controlled thyristor control breaking register that we discussed few classes back, all will introduce some sort of delay. Clearly, you see, if you have a thyristor device, it has firing angle. What is that firing angle? That is the delay. Therefore, similarly, and then there is AVR governor system, automatic voltage regulator governor system. There are power system stabilizer. There are voltage regulator. And just few minutes back, we discussed about the circuit breaker. Circuit breakers unit that introduce some delay because circuit breaker needs some time to open and we have to allow some time to get it reclosed. Clearly that is the delay. But those have some impact in the system. That's why you'll be getting many articles, 100, or if you just Google effect or impact of time delay on the performance of transient stability control in power network, you will get a lot of articles. So therefore, at this point, you forget about the cyber attack that may cause the delay. Just confine that there are lots of controller and they are communicating with the SCADA or other system, various control system for optimal reclosing purpose, and they will cause some sort of delay. Now, what is the impact of that delay on the transient stability performance? So that's why I had that some important question. What are the causes of time delays in electric power grid in general? And what are the effects? What are the causes? How the time delay is coming? And what are the impact? What is the effect? And how much delay can a system tolerate or bear without losing stability? And what is the method to minimize the negative or adverse impacts of time delay? These are the some important questions. So that we will be discussing briefly. So therefore, just take an example. You remember that few classes back we are discussing fuzzy logic control breaking register. Therefore, just take that example for the delay analysis. That you have a power network. That network has several generators, and that system has the transient stability control means. That means is that breaking resistor, thyristor base, and that is controlled with the help of fuzzy logic. And that fuzzy logic requires global input variable. That global input variable can be the total kinetic energy, or total voltage, or total active power, or total reactive power collected from the integrated entire system. Then what? How does it behave? That is the same. So that's why I take the example that we looked before, that you have a power network that has several generators. You have that fuzzy logic control breaking register that is maintaining transient stability. But in maintaining the transient stability, on the way, how it is confronting, how it is facing the time delays, that thing we'll be looking. So therefore, again, before I showed you this one of the example of the network, there are several fault points, but I said that point is the severest one. If the fault happens at this point, then the system goes unstable. This is the nature of the system, very unstable. There are 10 generators in that system. All 10 generators go out of step if the fault happens at this point. And then you put a breaking resistor at the terminal to maintain the transient stability. So you know that process, how the breaking resistor works. That is fine. Our talk is about the controller, breaking resistor controller. So that breaking resistor controller will need total kinetic energy information. That's why you see that G1, G2, G3, there are 10 generators. From all the generators, it will collect that. Here is, I have seen calculation of control input variable. I'm assuming that that fuzzy logic controller is here. That is taking total kinetic energy deviation. Total kinetic energy deviation means the definition is what is the total kinetic energy at transient state, then minus what is the total kinetic energy at steady state, normal condition. That is the difference. That goes to fuzzy controller. And then it produces firing angle and your thyristor switch works and braking register is activated. So you understand that. But main concentration is getting or giving the TKED to the fuzzy controller. So therefore you forget about this part. This is the controller. The main thing is collecting or calculating the TKED from this system. Then again the same process, because you need this signal to the controller. Again you have to go all the way, because all generators are not located at the same distance. As you can see, when a kilometer mentioned, from here to here only 100 kilometer, from here to here this is 100 kilometer, and everywhere there is some distance. And then of course, for example, as I said, for this specific system, point A is the most vulnerable, most critical. I mean, that is not only for this system. Keep in mind, every system has one critical point. Now, it may happen that that is critical, but all generators did not go out of step, only few. Or it might happen that none of the generators goes for the unstable mode, just they are oscillating. So therefore, critical point may be different depending on system. But for this specific system, if any fault happens at point A, then all 10 generators goes out of step. So that's why you must put on braking resistor here. Whatever at other places, or if you choose, no, I'll be putting one braking resistor at the terminal of each and every generator, that is okay. But you must need at least one braking resistor for this system, which is that corresponds to point A, I mean at this point, to maintain the stability. Now to apply that braking resistor with the help of fuzzy controller, what are the possible causes of time delay? That thing I am discussing. So therefore, as you can see, I assume that to control that braking resistor, I need TKD. And clearly, we already discussed there will be time delay. So therefore, based on this so we can generalize that what are the possible causes of time delays in power grid. So therefore, again, I have written time delays can be due to signal transmission through optical fiber or microwave, analog to digital conversion, online calculation of the TKD, and then time synchronization of signal by GPS. And then, as I already mentioned, some other factors might be related to the circuit breakers opening and closing operation following electric grid. And then, of course, there are AVR, governor, other voltage regulator, so many other devices. So naturally, there will be some sort of delay. And then again, I mentioned the other factors that cause delays, maybe from cyber attack. So at this point, you forgot this one. Assume that this is not the smart grid. Still, we're talking about the conventional grid, but still in the conventional grid, there are lots of automated controller and this type of controller that will cause the delay. Those are the possible causes of the time delay that we are talking about. So now we will see what is the impact of this delay. You understand that, okay, delay is coming because of this system, but how much bad it is, how much adverse it is for the system, and what can be the value. So therefore, again, as I said, if you just Google time delay, you will be getting lots of articles like impact of time delay on transient stability control. So you will be noticing there are varieties of reports, papers. So literature says that time delays may range from several microseconds to few hundred milliseconds. So it depends on the system. It depends on the controller complexity or what variable you are taking. That's why it can be several microseconds to a few hundred, 200, 300, 500 milliseconds. And then according to some report, typically 150 to 200 millisecond time delay values are considered to design some actual transient stability control bench. This is the like some realistic number. That this means that these numbers are pretty standard, considering 150, 200. But it depends on the system. This amount might not be enough. It might go beyond that. And then that value, for example, for a system, you calculated this range and you got 500 seconds or 200 seconds. That is the delay margin or withstanding capability of that system. So that's why I have written that each system has a specific delay tolerance for proper functioning. Some system can tolerate a delay 200, some system 300 or much higher. So therefore the problem that I am discussing here, I mean that this system, like I myself did some analysis and I found that if you go beyond 500 millisecond for that system, for this system, then the system become unstable or much more oscillating. So meaning that for that system, 500 millisecond is the delay margin or the maximum allowable delay. Therefore, keep in mind that every system has a specific delay. As I said, if you see the second bullet, some report says probably they have investigated subsystem. They said, okay, no, it should be around this range. That is enough to design some actual transient stability control means. But then I have seen some other report much higher value. And then I myself did some analysis for this system. I got up to, I went up to 500 millisecond. And I noticed if I exceed this number, then the system become unstable. So then I concluded that for this system, the delay margin is 500 millisecond. So, everybody, do you understand so far?
Yes, Dr. Ali.
Yes, sir.
Okay, very good. So then just some responses and then we will conclude and then our time is coming. Uh, for that system, the system that I showed you, the 10 generators, you see, system responses without time delay. So therefore, this is the fault response. As you can see, as I said, that point A is the most vulnerable. When the fault happened at that vulnerable point, I'm looking the load angle versus the time up to 20 seconds. Can you see? Initially, like all started properly and fault happened. It looks like all jumped. That's overshoot. Came back. If you are governor properly, keep in mind, if you are governor properly working, circuit breaker, everything in working, but still it did not help. It looks like then it were jumped up. And because there is huge hiccup, huge overshoot, to compensate, it came down. Then it went up and it never came back. And gradually aggregating. Gradually it is increasing. So by looking this on, and that is the reason, you see, I simulated this on up to 20 seconds. And now, what is the significance of this time? Because you are presenting your assigned articles or you are looking lot of papers, you will be noticing that sometimes some authors, they just show the result until 5 seconds. Because the transient stability point of interest is typically 5 seconds to 10 seconds. But initially, I was also looking until 5 seconds. And you see, if I see until 5 seconds, then I was not sure that it will come back or it will go unstable. And then I increase 20 seconds. That is the reason. And then I'm noticing like kind of around 10 second or 11 second, all are going out of step. That is the reason it is better always to look for longer time rather than just looking 1 second, 2 second or 5 seconds. Like if someone concludes for this system after looking 5 seconds, no system was stable. There was oscillation, but then that is the wrong thing. So that's why you have to look for longer time. So and then this curve is for the same all 10 generators, but by applying the fuzzy logic controller that we are discussing in this class, but still without time delay. In this analysis, there is no time delay consideration. Without time delay mean I assume that okay, nothing is happening. It is the ideal condition. There is no delay. Ideal time delay is 0. That was the assumption that I got. So now, so you see that was the curve, and now I assume that system response with time delay. Now, if you compare these two, in this case, I said with time delay of 500 milliseconds, and in this case, without time delay. This without time delay actually, this response. And then I am comparing two cases, considering time delay versus no delay. So if you compare, you see, it looks like until this portion more or less same. After that, you see, this became smooth. And here it is 20 seconds. I noticed until 30 seconds, all became perfect. It fully matched. But here in this system, I noticed until even 100 seconds, always like this thing is going on. Always this thing, never it came back to the original position. So those are like damaging. Those are detrimental for the connected system. So it cannot go in that way. So you have to return back to the original position. And that result I got considering 500, and then I jumped. I think I made several attempts. I went up to 750, and once I jumped 500, then much earlier again all went out. It became like that. So this means that it was going fine. Then at some point all went up because I considered more than 500 milliseconds. And based on that observation, I concluded here that 500 millisecond is I said it can be said the maximum allowable delay for this system is 500. This means that until that it is okay. If you go beyond that, then system will be fully unstable. This means that clearly that time delay has impact on the transient stability. So therefore, same thing. You remember, Lakshmi, you are presenting your paper. I think you showed one or two response that system was going unstable.
Yes, Dr. Ali.
You remember? So this is the thing exactly I myself did.
Mhm.
So yeah. So now, I mean, in 5 minutes I will conclude. Or I will stop the class. Now, as a power engineer, always it is better to quantify the results. Like you see, I'm comparing this versus this. Then you look, the first portion look like the same, and I'm telling that this is without delay. So anybody can wonder that how this is better. What is your basis of judgment? Because I can see there is oscillation, and again there are some oscillation here. But how you are claiming that this is better than this one? So therefore, as an engineer, not only you have to look the plot or response, you have to set up some sort of criteria, stability judgment criteria. You have to quantify it. So what is the percentage or what is the number as compared to this one? Then I can tell, no, this is better than this one. So that's why this is that quantification mechanism. For the evaluation of transient stability, the following stability index was used. You remember once few classes was I was showing you this equation, and I told this is pretty standard equation. It is doing d by dt, that W total. W total is the total kinetic energy, and then there is absolute value. It is integrating, then dt divide by system base power. Therefore, for example, system base power is 500, or for example, I think in this system 1000 MVA, is it 60 Hertz 1000 MVA base. So therefore, for every system, for 9-bus system, you notice 100 MVA base. Some system have 500 MVA base. It is 1000. So that is that number. It is going in the denominator. So therefore, ultimately, you will be getting the unit in second. And then the t I am integrating until 0 to t, because actually I am integrating starting from 0 to 20 these values, these load angle values. So sorry, the kinetic energy values. So and then while doing so, I will get some number. And then the smaller the value of WC, the better the system's performance. Because it involves the rate of change of W total, meaning that the better system will be when you will be getting the lower number. Like you got the result 2 and you got the result 5. The 2 is better. That is the meaning of this. So therefore, if I quantify by that technique, so everybody say this one, these are that fault point A, F, G, various fault points. I did for A first because that is the severest point. Now you see the rightmost column, everybody first, without breaking resistor. You see the number 238.917. So this means by using this equation, I got that number. Therefore, I simulated this case. I calculated for this response. That is giving me that number, 238.917, up to 20 seconds. And then once I am using the fuzzy control breaking resistor, everybody see these numbers are pretty small as compared to this. The same thing for F point or other fault point, these are without any control mechanism. That's why those numbers are higher. But once you are applying the controller, then you are getting a small number. So that is first observation. Second observation, because we are looking the time delay impact, here you see second column, when the fault point is the 3-phase to ground fault and time delay value, first I consider 20 microsecond, then 200, then 2. In that way, I have gone 500 millisecond, increasing gradually. Accordingly, see that with fuzzy control breaking resistor, I mean, I am applying the time delay when I have controller. In this case, you see, there is no time delay because there is no controller without breaking resistor. That's a very big number. Here it is controlled, this value much smaller. But what I am noticing, with the increase of the time delay, you see, gradually these values are increasing. This means why? Because the time delay has the impact. I am gradually getting the worst number. And as I said, once I jumped on beyond the 500, then immediately, not it is 50 or 60, it went like this number. That is the thing I told him. That although it looks like so, by considering 500, once I goes beyond this point, immediately like all out of step. Not immediately here, a little bit later. That's why I got very similar number. It was above 200, very close to this number. So this means that the time delay has the impact on the system. The same conclusion goes here and here. So that's why the overall conclusion is this one. The time delay associated with the online calculation of the input to the fuzzy controller has an influence on the transient stability part. Not necessarily only fuzzy controller or not necessarily only braking register. This is just a case study, example. It can be any controller. It can be any energy storage controller or other controller. If you need that type of input, total kinetic energy, total voltage, total active power, total reactive power, then definitely that will involve some delay. And that has the impact. And then, therefore, it is important to investigate appropriate control means to mitigate the negative effects. That time delay comes from fault, failure, cyber attack, or whatever the means is, or from the typical controller. So therefore, for this one also, as I said, that you will be getting 100 articles. Many researchers have worked on the time delay. Like in Lakshmi was presenting one paper, that is one author. Again, if you Google, this is my paper. I published another work in November 2008. Again, I was in Canada at that time. And this publication is IEEE Transaction and Control System Technology. So this is also very well-known paper. And there I analyzed the influence of communication delay on the performance of fuzzy control braking register against transient stability. What is the impact? So therefore, I must recommend you all, again, you download this one and then you read. So I think well over all the time. So is everybody fine?
Yes, Dr. Ali.
Yes, sir.
Dr. Ali.
Yeah. So therefore, the two read things: impact of time delay. First, you look impact of optimal reclosing technique on the system stability, and then followed by impact of time delay on the transient stability performance. And look the two things. And you Google, and then first you download my papers, and then you Google, and then you might get, these are kind of the old because it has been 12 years. You might get some recent paper also, the impact of time delay on the system stability performance. Okay, so with that, I like to conclude here for today. I'm stop sharing. So does